then we see where VD intersects ABC again. So we call this V, draw the altitude. Okay, so this is D. VD intersects it at U. So that's U. UM, M is the midpoint of BC, and then we see where UM intersects ABC. At X. And AX intersects BC at Y. A lot of intersections here. This is Y. It's not a super complicated diagram yet, but now it looks like it's going to get more complicated. Let YVM intersect it at Z. Okay. Try to make Z. Oh, that's interesting. If we vary V, then it looks like Z is always the same point. So maybe that will help tell us something. But I promise I just noticed that now. I did not worked on this problem yet. So this is okay. So basically, first we could maybe try to show something about Z. Is Z the antipode of A? Let's see. Because then this is really just like oh my goodness. So first is just showing Z is the antipode of A. And then once we show that, Z prime is the reflection of Z over OH. This is really two problems in one. First shows Z is the antipode of A. I'm guessing H is the orthocenter. That's the orthocenter. We reflect Z over OH. That looks so silly. Just, okay. So Z prime lies on the circle then. And then the circle Z prime OH intersects ABC at T. And then we want to show that TZ passes through M. Okay, so we really have two problems in one, right? Let me make the diagram look nicer. Problem one, show that Z is the antipode of A. And then problem two, prove the rest of the problem. And then we can hide a lot of the diagram. Okay, so let me start out just trying to prove that Z is the antipode of A. And then we could deal with the rest of it. All right. So U, D, and V. What did I do after that? So Z is where Y, V, M. Is there anything else I need to draw here? UM, I need to draw UM. And it intersects it at X. Okay. AX intersects BC at Y. Okay, so first let's try to show Z is the antipode of A. That would mean ADB is similar to ACZ, so we would have a spiral similarity. Interesting. So yeah, O doesn't lie on the circle, so I'll try to make it so that it doesn't look like that. Maybe something like that. If I make V lower, then it's obvious it doesn't lie on the circle. Okay, so we want to show ACZ is 90. Or we could define Z as the antipode. That's probably a better way to do it. Just define Z as the antipode, and then we want to show that it's cyclic. I like that better. Or I could call it Z star. Why not? So we could say let Z star be the antipode of A. And see, oh, it doesn't like that. Z, I don't know. Does that work? No. Z plus. Let's try that. Doesn't like that. Dang it. Z. There's got to be some Z wiggle. It's probably not going to like that. Z prime. I don't know. Z double prime. We'll go with that for now. I thought there's a way to do Z plus or something like that. All right. We want to show that this is cyclic. YVM Z double prime. And we have a couple spiral similarities. Let's see. What's the best way to do it? Can we use power of a point? These, I don't think those concur. No. We could try to use power of a point. We could try to do an angle chase. So one way we could let these intersect, we could try to show ME times MY is VE times EZ double prime. I don't know if there's some other circle going through ME and Y. Not sure. It's hard to tell.
Should we actually prove the later part of the problem first?
Oh, really?
Suppose that Z is the antipode and then solve the problem. I don't think it looks hard.
So, okay.
It looks easy. Yeah.
So given that this is the antipode, then try to show the rest of the problem.
Yeah, since you need to show that TZ passes through M, but but actually line ZM passes through H. That is well known. So T is the AQ point, and then everything looks like pretty simple.
Okay, so say that one more. So T is assuming Z is the antipode, if we reflect it over OH, what was the first thing you mentioned?
If we wanted to have TM and Z collinear, then T would have to be the AQ point.
Okay. Yes.
And then passes through H. So we could define T as ZH intersection of circle, and then just prove we have this cyclic thing.
And then prove that this is cyclic. Yeah.
Yeah.
Okay. And then to do that, let's see. It's probably,
Maybe an angle trace, yeah.
yeah, because there's a symmetry here, because angle ZOH is 180 minus like half of angle ZOZ double prime, which is 180 minus angle ZTZ. Yeah, so that proves it. So yeah, the second half we've solved.
So we just need to prove Z is the antipode.
Yeah, then that would solve it. Yeah, ZT or yeah, ZOH Z prime OH is 180 minus half of Z prime OZ double prime, which is 180 minus Z prime T Z double prime. Yeah, so that solves it. So yes, you just have to show Z double prime is equal to Z, which is the same as showing VYZM is cyclic. And yeah, it looks like these concur, but they don't actually concur, I'm pretty sure. Yeah, so VYZ double prime M. Or V can really be any point. That's interesting. So let's see, if it was cyclic, then what could we say? What would be the easiest way to do that? We have to use M as the midpoint. Maybe we could reflect this circle over the perpendicular bisector BC, because then it would pass through the foot of the perpendicular. So let's see, if I do that, what happens if I try that? So I reflect it. It's going to then pass through this. Yeah, but I don't know where Y would go. That's the thing. Maybe it would. It's probably a bad idea, but I'll just try it for a second. Oh, maybe these are collinear then. Yeah, it looks like it. So maybe it's not such a bad idea. And then this would go through here. Okay, so V would go to F. And interesting. I mean, T, we kind of constructed T later in the problem. So yeah, I don't know how helpful. I don't know if it's really that helpful that those are collinear. Yeah, I don't think the fact that these are collinear really helps much. Although maybe it would help. So then if we want to show this as cyclic, and H doesn't lie on the circle. So I was going to say maybe we could show TF times TE as TH times TM. But that won't work. I'm probably overthinking this, but I don't mind. So angle FGM, it's angle FGA plus MGH, and MGH is MHD. So that's probably not hard to calculate. We need to show that's angle FEM. And that's angle FEM is angle TFV, and FV is parallel because FV is parallel to BC, which is angle T. Okay, so we want to show angle TFV is equal to FGM, and FGM we can like calculate as interesting.
Did you solve that part, or you just had some progress?
I just had some progress, but I think this might lead to a solution. So FV.
Well, I solved it using Butterfly Theorem, but
Okay, yeah, let's do that's probably a better way to do it. So should I hide this circle?
yeah, I don't need that.
Okay. All right. All right.
Okay, reflect D over M.
Okay.
So you can probably now see how we will use Butterfly.
Yeah. So
By Butterfly Theorem, VM and XD prime concur on the circle.
VM and XD prime. Okay. Okay. Hold on 1 second. So okay. It almost looks like they're parallel, but I don't think VM and XD or UV and XD prime are parallel, right?
No, they shouldn't be.
Okay.
Okay, so Z prime is defined as the antipode, just like in the picture. And we want to show that the Z prime lies on the circle. Okay, so it is like obvious that the Z prime D prime is perpendicular to BC.
Okay, so this point Z double prime, it's defined to be the antipode. So it's so from there it's obvious that it's perpendicular.
Yeah. That is because H and O are the isogonal conjugates. So
Yeah,
basically, it is very easy to prove.
yeah.
And because AZ prime is the diameter, we have that Z prime XY is 90 degrees.
Okay. So
So
yeah.
we have a secret.
All right.
Then we can just do basically an angle chase and finish. So angle MVZ prime,
Yes.
that is IVZ prime,
Okay.
which is IXZ prime,
Okay.
which is D prime X Z prime.
And then this is cyclic. So
Yeah.
that's also. All right. Interesting.
So yeah, very, very quick solution. The
Yeah.
only like non-trivial part, which is not an angle chase, is using the butterfly theorem.
Yeah. That's the key to it. All right. So I'm going to call it Z double prime. So I know it's kind of annoying, but because there's another Z prime later. Be the antipode of A. So we're going to try to show Z double prime equals Z. Let D prime be the reflection of D over M. And then Z double prime. So Z double prime D prime is perpendicular to DC by symmetry. I think that's easy enough to understand. So and that implies that y equals Z double prime XY equals 90, which means that Z double prime D prime XY is cyclic. Now we can use the butterfly theorem. By the butterfly theorem, Vm and xt prime concur at a point I. Vm and t prime concur at a point I on ABC. And here it's just angle chasing. And then we want to show that this is cyclic, which will show Z double prime equals Z. And that is an angle chase because we are going to show that I think BMY is, hold on one sec. So, okay, so XD prime Y is XZ double prime Y. Okay, so we're calculating MY Z double prime in two ways. So MY Z double prime is D prime Y Z double prime, which is D prime X Z double prime. Yeah, which is I X Z double prime, which is I V Z double prime. So that solves it. Okay. So Z double prime is angle D prime. D prime X Z double prime, which is angle IX Z double prime, which is angle I think it's IV, right? Yeah, IV Z double prime. I'll split this into two lines, but it's IV Z double prime. Z double prime. And this implies, so I'll just split into lines. This means that MV Y Z double prime cyclic implies Z double prime equals Z. That's the first part of the problem. And then for the second part, it's just an angle chase. So angle Z, by symmetry, angle Z prime OH that's going to be 180 minus angle Z prime OZ over 2, which is 180 minus Z prime TZ over 2. Oh no, it would just be Z prime TZ. And this implies that Z prime, oh, well, we're defining T differently. So, yeah, so let ZM intersect the circle at T prime, then it's well known that A T prime H equals 90. So let ZM intersect ABC at T prime. It's well known that angle A T prime H equals 90. It's and that it passes through. Do we even need the orthocenter? Yeah, we do. So I'll just say it's well known that ZM T prime passes through H, and yeah, it would be well known that, I mean, it's clear that it's 90 because Z is the antipode, so we don't even really need to write that. But this and then this implies that Z prime T prime Z prime T prime OH is cyclic, and that implies T prime equals T, which implies TZ passes through M. Okay. All right. I think we're good with that. Okay. And let's move on to the next one. So that was a fun one. We have about an hour left. We could do any one of these three. I'll just start with this. So ABC has circumcenter O, and then N are the midpoints of AB and AC, and then we project O onto that. Seems easy enough. We have our midpoints, M and N. M and this is O. We have T and D, so these are easy points so far. So D will be this point, and T will be this point. And why not just make a rectangle? Seems like this might be a useful rectangle. So I'll call this P. And why not just call this something else? So this would be the midpoint of AD. We can call it E. Okay, so we have a rectangle. Let TD intersect the circle BOC. Okay, so we have this circle, and sometimes it's useful. So when you have this circle, it's useful to draw the center. So I'll have to shrink the diagram a little bit, but it's often useful to draw. Yeah, I hate having to shrink it that much. Let me make this a little taller of a triangle, and then I won't have to shrink it so much. Okay, because basically I want to draw. The reason why I want to do that is I want to draw this point because OF is a diameter and FB and FC are tangent, and that often helps. Okay. So TD intersects the circle at points U and V. Doesn't say which is U and which is V, so I could do whatever I want, I guess. And AUV, we have another big circle, unfortunately. AUV intersects MN at 2 points, X and Y. So we could, doesn't say which is X and which is Y. So X, but it's X and Y. It almost looks like this is a rectangle. Let's see. ATYOV. I think it is probably. And by the radical, it looks like, yeah. So this is a kind of similar thing where there's like two problems in one. But the first problem doesn't look very hard. So AY intersects AMN at a point R. And AX intersects it at S. And then we want to show AO, RS, and MN are concurrent. Okay, so again, this is like a two-step problem. It's hard to see one of the intersections because, yeah, those circles are tangent. So AMN is tangent to ABC. Let's see if I can make it easier to see that intersect. It's not easy to draw it. There we go. So that's R, and then this would be S. I'm going to rename it in just a second. That's S. So this would be R, and so first, let's try to show TOVY is a rectangle. Which looks to be true. Oops. We want to draw a segment TD, and TOP, and we don't know yet that these are all collinear, but if we could show this is a rectangle, maybe it won't be that hard. So let's see. Let's make sure that's really true. I move things around. But look, I don't know if it looks true, but let's see. YV. Oh, I don't think it is. No, those are not parallel. Because I was going to say, by symmetry, wouldn't YUOT have to be a rectangle? So, okay. So we want to draw AY. So maybe it's not two problems in one. But maybe, let's see. Looks like those lie in a circle. Don't know if that's obvious. So if TY, if it's true for S, like whatever is true with V, you would think would have to be true with U, right? So TOXU, is TOXU cyclic? It looks like it, and it looks like that also passes through R. Okay, so trying to make it look a little easier to understand the diagram. I'm not going to draw that bottom point. We'll just have to keep it in our head for now. That there's that sort of bottom point. Yeah. Okay. So yeah, these circles are orthogonal. Well, is that right? No, I don't know if you can say they're orthogonal, but all right. So first of all, is it obvious that these are all cyclic? Obviously OTY is 90, but is it obvious that OSY is 90? We drew AUV. So AO would be a diameter of this circle. So is it obvious that these points lie on that circle? By definition, R and S lie on that circle. Okay. So we know that AO is a diameter of this, so from that it follows that angle YSO is 90. So we know that YTOS is cyclic. We don't know that V lies on it. So, but we know that YTOS is cyclic, and we know that XTOU is cyclic. Okay. So can we show V lies on YTOS? It looks familiar. So I think that might be an angle chase. So we want to show angle OVY is 90. Okay, YTOS. So angle YTO is 90. And then also, if you look at this circle, through AM and N, AO is the diameter of that circle. Because this circle is homothetic to the whole circle, because it passes through M and N. So AO is the diameter of it. So angle ASO is 90, so angle YSO is 90. So since YSO is 90 and YTO is 90, YTOS is cyclic. Does that make sense? So can we show YVO is 90? So YVO is 360 minus BVO minus BVY. And for BVY, let me calculate that somehow. So BVY is UVY minus UVB. Oh, it looks like BV and N are collinear and CV and M are collinear. But wait, I'm not sure that's true actually. If I move the diagram around, that's not true. Okay. But angle YVT is angle UXT, which I'm trying to see if I can just do an angle chase here. UXT is UXY UXT is 180 minus UOT. It's interesting. So we want to show that UOP equals YOT. Okay, so I think what we want to show is that OY and OU are like isogonal. So angle YOT is angle UOP. Let me check that that's true. So this would be that angle, and then this 57.9, 57.9. Yeah. So we want to show OY and OU are isogonal. And maybe we can use projective geometry for that. Not sure yet. Maybe there's a different way to show V lies on that circle. So could V be the Dumpty point? Let's see. So how do you define the Dumpty point? I forget. So I think if it was the Dumpty point, no, it's not, right? Because then AC would be tangent to ABB. So yeah, we want to show YOT equals UOP. We want to use that this is a rectangle right here. So if this is a rectangle, maybe we could think about it a different way. We want to show V lies on this circle, but V lies on TD. We want to show angle VTO equals angle VYO, or we could try VSO. And VTO is like a whole bunch of different, there's like 4 different ways to think of VTO. Now VYO is VYS plus SYO. And VYO. Let's think about that angle. VYO. So VYS equals VXA, which is BUA, which is VGA. I wonder if OY and VG are perpendicular. So here's OY. I don't think they are. No. Maybe there's one more cyclic quad we have to find. Obviously, TEDP is cyclic. Does anything else lie on that? So it's kind of like we want to show that these circles are homothetic, right? Because if this, okay. So actually, are these, I don't think these circles actually are homothetic, right? I think they actually intersect somewhere. Yeah, they're not homothetic. To show that V lies on it is a little tricky. I wonder, you know what? I wonder if YV and O and this meet. Oh yeah, if the problem is true, then these would meet on the circle. So I really do want to draw that point back there. I want to show that YV and that point are collinear. It's making it hard to draw a good diagram. I want to show that YV and F are collinear. How should I draw this to best? Okay, so how do I show Y, V, and F are collinear? Could I use the radical axis theorem somehow? So if Y, V, and F are collinear, then X, U, and F would also be collinear. It almost seems like we first want to prove this is cyclic and then show they're collinear. Right, because then we would have these are collinear and this is collinear. Maybe we could work backwards a little bit. Maybe we could define V to be the intersections of these circles. Yeah, maybe we could let U prime and V prime, instead of saying TD, what if we let U prime and V prime be the intersections of those circles with BOC? I kind of like that better. And then we want to show that those are collinear. That seems easier, right? Yeah, to me it seems easier. So we could call this U prime. That's the intersection of this circle, X, Y, V, A, and call it U prime and V prime. So this would be YTOS, and the other would be XTOR. And we let U prime and V prime be the intersections of those circles. And then we want to show TV prime and V are collinear. And then similarly, TU prime and V would be collinear. So now we can do angle chases. We would know that these are collinear and those are collinear. And then we would have so we know angle YOT. Well, sorry. We know that this is a rectangle. We want to find angle V prime TO. That would be V prime YO, or sorry. So we have this. B prime TO. Is V prime YO, which is YOT minus YFT. Yeah, how do we find that? What is Y? Oh, we would have to make this Y prime then also. Because Y is where AUV. Yeah, so this would be a little tricky because we would have to make these X prime and Y prime instead. And if we did that, that would still be okay. So it would be where AU prime V prime intersects them. X prime and Y prime. Okay. Oh, but then how would we define this circle? Actually, yeah, I'm not sure we can do this because yeah, I don't know if we can do it the way I'm thinking about it. You guys want to keep working on this problem?
Yes, I want, since I actually have a different idea.
Okay.
I think than what you did. I could share what I thought.
Okay.
So this thing we want to prove AO, RS, and MN are concurrent. That is equivalent to having an involution at that circle AOMN, which swaps R and S, A and O, and M and N.
Okay.
And you can project that involution through point A on
Okay.
line MN. And then we would need to have an involution. Actually need to draw in two new points on that line. So intersect AO with MN and tangent at A with MN.
Okay. So let's see. AO. And I can draw the tangent. And this is going to be tangent to both circles, obviously.
Yeah. Okay, so you project that projection takes R to X and S to Y. So we will need to have an involution which swaps X and Y, M and N, since M and N stay the same, and I and J, since A goes to J and O goes to I.
Okay.
So this means we would need to show there is an inversion at that line, which swaps these, and that is just equivalent to having that circles AXY,
Okay.
which is already drawn, AMN and AJI are coaxial.
Okay. AJI. Okay. So we want to draw the intersection point of those two circles and then try to show that it's cyclic. Okay.
Also, just another thing which is useful in this problem is that dt passes through the point which makes an isosceles trapezoid with triangle ABC.
Okay. So then maybe the mixed linear, I'm kind of going ahead here, but that could, mixed linear and circle could be useful.
No, mixed linear doesn't.
Doesn't do anything.
Yeah. And I proved this that then that AL is parallel to BC.
Okay. And they would meet on this circle right here.
Yeah. Also, something which I didn't prove but just looked like true is that KI and Q are collinear.
Okay. Interesting.
Also, it is easy to prove that AJDI is cyclic.
AJDI. Okay.
Yeah. So you would actually not need point D. You would have to show that ADI and those two circles are coaxial
Okay.
at the point K.
ADKI.
So I believe this is quite different from what we were doing, right?
Yeah. So we'd want to show that the circumcircle of ADK, let's think, ADIK is cyclic, or let's see.
Yes, ADIK.
So then you just get rid of J. Is there some other point it passes through? Is it tangent at D? No. Is this tangent to it? Let's see. No. So we could try to show that AE times ED is JE times EI. Oh, but that would leave out K. That's probably how you, oh, you showed AJDI is cyclic, right? Just have to show K. I wonder, so if I draw this point in again, F, I wonder if F and A are collinear with this point right here. We'll just draw it in. And yeah, that's kind of obvious actually. So we could try to show that WA VY is cyclic. So yeah, I'll just make it bigger. Just remember that. No. Let's think about that. O. T is that W times that A. Now I'm confused. Oh, I see. I'm thinking about using inversion. Oh, I think I might have an idea here. So I think I might be able to prove that V lies on this circle. So angle YVO equals, I had an idea, but now I think I might have lost it. It's UVO plus UVY. Yeah, so even if we don't know that this, it's like 2N is rejoining, even if we don't know that line exists, YVO is going to be, I think it might just be Meckel's theorem. Because we know this is cyclic. And we know that this is cyclic, right? So by Mikkel's, oh, it's just Mikkel's theorem, I think, that proves that this is cyclic. Because we know UVOC is cyclic by definition. And how do you define V? Okay, actually, I think we know that UVOC is cyclic. Yes, by definition. And we know that this is also cyclic. AYGX or YGUX. So then by Mikkel's theorem, TYOV would be cyclic. But how do we know YGUX is cyclic? So AUVX is cyclic. Yeah, we don't even need that. We just need YVUX is cyclic, which is because here it's saying AUV intersects it at X. And then, okay, so AUVXY is cyclic. Yeah, by Mikkel's theorem, we know that Y lies on this. I was making it too hard. We know that this circle's cyclic right here. And we know that YV and that point are collinear. Then once we have that, we want to show AO RS and MN are concurrent. Maybe we could use the SARs. So we have AMR and SON. And AR and MN meet at X.
I think inversion might work. I did a root BC inversion.
Okay.
For that main idea that you have to show that those three circles are coaxial. And then you need to show that three lines are concurrent and the picture doesn't look too bad.
Okay.
Basically, everything inverts to quite normal points, except a few, which are hard to work with, but I think it is easier than this picture.
Okay.
I'll try to do it.
So let's see. So you're doing a root BC inversion. which often works pretty well with like circle BOC, I feel like. So, okay. Often I feel like using Pascal's theorem is a good way to show. Sorry, I keep going all over the place. You can keep going with your idea. Let's draw the center of the circle. So if we do like RA, so ZO is tangent to that circle. That might help. So let's see. Oh, I'm just trying to use Pascal's. AOMN over Q AN. So I would be collinear with those points, although I don't think it does much. Yeah, those are collinear. Is there a better way to do this? AMZONR. We could try that. Yeah. I feel like this is one of the like we did a problem in the last session where you used Pascal's a whole bunch of times, and I think this might be able to be solved in a similar way. I guess another thing, yeah, we could try to show I lies on the radical axis of two circles, which is, I think it's kind of like what you're doing. So we would need another circle passing through R and S to do that. So actually, maybe we could even use the 9-point circle here. So we could define I to be the intersection of RS and MN. And then we want to show I lies on the radical axis of these two circles. It's one way to do it. Yeah, these circles are reflections across each other. So basically, I wonder if we reflect S across MN, is it that point? No. But yeah, your inversion idea, we want to show AJKI is cyclic. And we know D lies on, we know AJDI is cyclic. Is there another circle that passes through those? I don't know. Oh, that's kind of interesting. It's like these points all line a circle, R, T, S, T, and J. Yeah, that looks pretty useful. So, all right. So we are out of time. I'm not sure if, yeah, Stefan had to hop off, but I bet there's probably a way to do this, like with either the radical axis theorem, or Pascal's theorem or something. All right, so I will keep working on this, but thank you both for yeah, staying on. So for anyone watching, thanks for watching. If you would like to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day. See you next time.